lecture. And so basically we are going now over the final exams. For those who are listening to the record and missed it, we are going over the course syllabus. And so we will have the final exam. We are talking about the short quizzes. They will be weekly, but we said one lecture will be less, one exam will be less involved, the other exam will be more involved. As I just gave your friends an example, one will be similar to an exercise we solved in class. The other week it will be more involved, involving more lectures. And so the short quizzes will compensate for the midterm. In a sense, there will be no midterm questions. Yes, Abdullah, if you can type your question, that will be great. I'm waiting for you to type. Yes, let me, I remove the participant. Thank you for, okay, next time I will remove the waiting room. Let me just also take care of one. Okay, thank you, Abdullah. Okay, so the idea is that there will be the best 10 tentatively out of 12, and the assignments will consist mostly of piece-by simulation. Submission is on Moodle, and there will be late submission penalty, but try your best to submit your work, and don't give up. It is your grade, you deserve it, so work on it, please. Okay, so now we will start talking about the course. So let us look at these gadgets. These are electronics gadgets that you are very familiar with: the phone, the camera, the computer. We all are familiar with them. The question becomes is how we can come up with a system. What are the basic building blocks of any system? So if we go to any engineering company and we look at how we go through this system, it all starts with an idea, but then the idea needs to be realized. And in order for the idea to be realized, we need to have an army of engineers. So for example, we will have the architect who tries to build or envision the system. We will have the software engineer who will try to write the applications that run on the system. And we will have maybe the physical design engineer. And this physical design engineer is the person who is really responsible for implementing or building these, the blocks of the system for it to be realized or to work. So what we are going to learn in this course is we are going to learn about the basic elements. And just like the cell is the basic maybe component of the human body or the building block of the human body, diodes, transistors, and other little gates are also the building blocks of these gadgets that we use every day. So just take something for fun to you to know, a step back into history. The first computers were really people. So just like there are today, there's a teacher, a doctor, an engineer. They used to bring those ladies who would sit down and do all of these calculations manually, hour after hour, day after day. And they called them computers. And human beings are prone to error, just like today's machines are also prone to error, and but at a higher rate. And so in the World War, they decided that they need to build something more reliable in order to do these calculators or computers. And so I think it was at the University of Pennsylvania or somewhere in the US, they relied on vacuum tubes, which are like big light bulbs, in order to start to build rooms that were called computers. Okay, so this is called ENIAC, Electronic Numerical Integrator and Calculator, and it is interesting for us to know that now we are on the verge of the quantum computing age, and whatever were the vacuum tube computers at that date, which were so bulky, and now we have those little chips that are smaller than the coin that have millions of transistors on them. Today, quantum computers are this bulky. They are like big chandeliers that have coolers that are trying to deal with 15 or 20 quantum bits. And we are hoping that we will have the jump to having small quantum computers soon. Hopefully, if it takes at the same time scale, if human beings are that aggressive, then we can also have another jump into a new technology that will take us to even better compute. So what I'm trying to say is that in a sense, you are lucky that you are living, now you are heading to the quantum computing age, and hopefully what we learn in the electronics domain will inspire us to work on more recent technologies like neuromorphic computing and memory compute, and people now are doing all those innovations to mimic the human brain and to enable exponential computing power. Of course, there are limits, but when there is a way, there is always a way. So, okay. So, what do we want to say on this slide? If we did not live in the current technological age, we would have had to send our signals or perform our communication in a different way. And luckily, we live in the information technology age, so we have advanced the technology so much that we can communicate a large bunch of data. Now, the question is, what does electronics have to do with all of this data? So, in the information technology age, what we have to do is we are really collecting all this information around us. And information is really exists around us as signals. Signals meaning my voice, the motion of Earth, the TV signal, the radio signal, all of these signals are carrying information. And typically the natural signals which we try to collect, like the seismic or the voice, etc., these exist as low power signals. And if I have maybe few milliwatts, because of course, if we can with our voice turn an engine, then this would be a miracle, right? So what happens is that we need electronic circuits in order to capture those signals properly, like an amplifier. So for example, if I am talking here into the amplifier, into the microphone is a transducer that is going to transform my voice, which is the waves in the air, into electric signal. So it transforms it from one form of energy to another, like the sound to the voltage. And then this small signal, which is a few millivolts, is going to go through an amplifier, which will magnify it. Okay, now if I'm connecting this to a phone, then this is going now to process this signal. Yani it is going to take it after the amplifier, quantize it, and then process it on the chip, maybe store it, refine it, keep it for later, or if I want to send it to another phone, process it, then envelope it, and then send it through the antenna. So we need in the middle those amplifiers and then those processing circuits that are going to amplify my signal so that it can be processed and then it can be sent over the air to someone. Okay, and the same applies when we collect all of these signals in order to apply signal processing to them, in order to store them for later use, etc., etc. So this is where electronics play a key role into translating the information that we have around us into the world into information that can be processed, transmitted, and utilized later. Okay, so I'm going to stop sharing this screen now, and I am going to now share a slide which we are going to practice on. So once I claim this here, um, uh, so from today on, we are going to have the lectures just like we are writing them on the blackboard. I'm going to write them here on this screen. I will then save it and hopefully upload it as PDF into the Moodle page, along with a link on YouTube to the recorded lecture. Okay, so today we will have the style. If you like to write along with me, feel free to do that. And I will try to make those notes as clear as possible. And the reason we do not prepare slides in 310 because we think it is better to walk you through these new circuits slowly, draw them slowly so that you get accommodated to them. Okay? And our first lecture, therefore, is going to be about amplifiers. So the first lecture is going to be about amplifiers, and we will now try to refresh your memory about amplifiers, which I think you took in ECE 290. So the basic idea is that an amplifier takes a signal, okay? It takes a signal and gives us a stronger one, okay? So it outputs a stronger one, okay? Now to remember what's the symbol of an amplifier. An amplifier is like a triangle. So it is a triangle and it has an input. So it's a two-port amplifier. It has an input port and it has an output port. So this is its input and this is its output, and this is our amplifier circuit. So this is the symbol that we will use from here on. From here, we will have a weak signal. And from here, we are going to output a stronger signal. Okay? And in order not to keep drawing the amplifier always like this, we are going to draw it in a form where we will have a common terminal, and this common terminal will be the ground. يعني أحسن ما نحطه 2 ports, we will draw it with a common terminal where the common terminal is the ground. And so this is our amplifier with the common terminal, which is the ground, okay, which can be considered, it is shared by both input and output. And then we will have here the input port, and we will have here the output port for the amplifier. Okay? Great. Now, if we want to look at this voltage amplifier, the input signal can be a current, can be a voltage. So what we are going to first introduce is the voltage amplifier. So the voltage amplifier it takes as input a voltage and its output is also a voltage. So the input and output are voltage signals. Okay? So for this amplifier to operate, we will need, we will need not only to have the input signal, but also we need to have a DC supply. يعني my amplifier is going to have the input port, which brings for us a small signal, it will also have the output port, which will amplify the signal, and it will also need to have a DC supply to power it on. And this is the ground, this is the in, this is the out. So we are going from here on to call this plus or minus Vin, and this is plus or minus V out. And also we are going to need a DC supply, because power does not, or energy does not come from vacuum. The small signal is in millivolts. It's being amplified maybe to hundreds of millivolts. So it will take its energy from the DC supply, which is feeding the signal. So this is called VDC. Okay, so this is the DC supply of the amplifier. Now, this amplifier is characterized by a gain, which is such that VO is equal to AV times, or V out is equal to AV times Vin. And so basically this gain AV is really, this is the gain, so AV is the gain of the amplifier, and the gain of the amplifier can be positive or negative. So the gain can be positive or negative. Yani I can have positive gain or negative gain. Now, typically, the amplifier is going also to drive a load. Yani the signal which I am going to send has to be sent somewhere. So it is going to drive a load. Maybe it's a resistor load, or load, maybe it's another amplifier, so that we can cascade many stages and so on. Or maybe it is just the wire that is transmitting the output signal. Okay, so anybody has any questions so far about amplifiers? Okay. Okay, so in order for this amplifier to work, meaning for amplification, the magnitude of AV has to be greater than 1. If it is less than 1, of course, it will not be amplifying. The unit for AV, if I have a voltage amplifier, is volts per volt. And the definition for AV is VO على V. Or V out over V in. Sorry. It is V out and V out over V. Okay, or VO over Vn. Now, one thing that we need to be very careful about, okay, note that V out and Vn represent the small signal portion of the voltage signals. Yani, note that in this equation, in the AV equation, okay, V out and Vn represent the small signal voltage portion of the voltage signals. ليه؟ لأن later we will have to bias the signal, and really only the sinusoidal component amplification is what we see in the AV, and we have some DC component that does not get amplified. Okay, so this is a very important note, لأنه usually students get confused about it, especially in the questions that we post for you later in the short quizzes and in the midterm or the final. Okay, so let us take an example now of a signal that we are drawing. So let us say that if I have the input signal Vn okay, as function of time t, and that Vn as function of time t is a small sinusoidal signal, okay, let us say with amplitude equal to A, okay, so Vn is equal to A sine omega t, okay, and let us now assume that V out has some gain with respect to Vn such that AV is equal to minus 3, okay? So if AV equals to minus 3, then V out in green is going to have a magnitude 3 times that of Vn, but it will be out of phase because it was multiplied by minus 1. So if we draw V out, it's going to have this form, and this is not exactly to scale, and so this is going to be equal to minus 3A, okay? So basically, V out is equal to minus 3A sine omega t. يعني when Vn is max, V out is min, and vice versa. Okay, let me see your questions. Yes, I will admit them. 1 second. Thank you, Karima. And Nidal, you are asking a question regards, sorry for the interruption, what do you mean by small signal portion? Yes, this is very important note if you have forgotten it. So let me insert a new page and we will draw what we mean by small signal. So what is a small signal? If I have a certain circuit, okay, where I have a signal V n of t, it's going to be equal to little Vn of t plus big Vn, okay? Now, what we mean by the big Vn is that this is a DC component, okay? And this is the small signal component. And let us try to see how our signal will be. I will give 2 examples. The first example is I have the signal, my signal Vn as function of time, where it is equal to A sine omega t, just like the signal we just saw. Okay, so if this is equal to A sine omega t plus 0, okay, is my Vn of t, this means that my DC component is 0, and this means this is my small signal component, and from here I will put SS for this small signal component. يعني السيجنال اللي عندنا اللي بتكون لها primary component which has a small portion and small value، مثلا 1 millivolt، بتكون هذه هي carrying الانفورميشن اللي انا بدي اياها. ليه هلا هون this is 0 يعني as if this is my voice. Okay, and then we can have another signal, for example, where the DC is not 0. يعني أنا okay, if I have a certain signal that is Vn of t, okay, which is equal to A sine omega t plus 2. Okay, in this scenario, my signal really, when the sine omega t is 0, okay, my signal is going to be equal to 2, right? And when sine omega t is max, my signal is going to be 2 plus A, and when sine omega t is min, I'm going to reach 2 minus A, and so on and so forth. Okay, so this 2 volts, we call it the DC bias. Okay, يعني we have shifted the signal up with a DC bias equal to 2 volts, and this portion which is carrying the information is the small signal component of my signal. Okay, now what happens in amplifiers for them to operate, we will notice later that we will need a DC bias for amplifier to work, for the amplifier to work. يعني later we will teach you that we need this bias in order to be able to amplify, to push the signal to that level. But the portion that will be amplified, this is the portion that gets amplified. So this is the portion that gets amplified. Okay, and this is why I told you that when we talk about the gain applies here to the small signal component, okay, of my signal. Nidal, is that clear for you? Anybody has any questions about the small signal? Okay, I'm assuming it is yes. Okay, so now that we have spoken about the small signal components of the circuit, we can now, just trying to insert a page here, we can now continue with the lecture material. So we have inserted here on this slide a small signal analysis. What is my small signal? And we were talking about the amplifier, how it works. So this is a note page. Okay, so the amplifier amplifies the small signal component of my input signal. This here we showed, and thank you, Doc, we showed that we have negative gain and we can also have positive gain. So if AV is equal to +3, okay, so if the gain AV is positive gain, in this case my output will be plus 3a sine omega t, and my output is going to look something of this sort. Okay, so depending on the gain, my output can be in phase or out of phase with my input. Okay, so now we will continue moving on to the next page, set of materials. Okay, so the peak for V out, okay, so if we want to explain this again, just as we have in our notes from previous years, therefore the peak of V out is equal to AV divided V max, okay, when Vn, if Vn peak is equal to Vmax, okay? And the question is, because sometimes you get a question, what is the peak-to-peak value, okay, of V out, for example, when AV, let us say, is equal to -2 and Vn is equal to 0.3 sine omega t. Okay, so this is an example question, and in this case, the example answer will be the peak-to-peak is really 2 times AV times Vmax, and it is absolute value because it's a peak-to-peak value. So this will be 2 times 0.3. So this will be 1.2 volts. Okay, so this is an example of peak-to-peak value and the peak value of the voltage. Okay. So now that we have seen the signal as function of time, a very important characteristic function that we look at is the transfer characteristics of the amplifier. Okay. So the transfer characteristics of the amplifier, just like any transfer function, really, just like any transfer function, properly, just like any transfer function, they show me the properties of V out versus, يعني on the x-axis I will have Vn, and on the y-axis نبقى في عنا time axis here, I will have V out. And the reason why we need to have the transfer characteristic of the amplifier is to be able to answer for what range of Vn I can have gain and what is the value of the gain. So we will first start by a basic, very basic straight line that is passing through the origin. So if these are my transfer characteristics, okay, so if I have a line passing through the origin, okay, then the slope of the line will be equal to the gain AV, okay? Okay, so if this is with gain equal to AV, this represents a plot of VO versus VN, or V out versus VN, V out or VO versus VN. Okay, and not always I can have a line passing through the origin, but this is the first example. In this case, this line has a positive slope. Okay, so this is a positive slope. And in another example, I can have another line with a negative slope. So this is a negative slope. Okay, so AV in this case is going to be negative. Sometimes we might have alternate gains where the gain becomes slightly more complex and it does not necessarily pass through the origin. And we will talk about this later as we take more examples. But now let us first introduce the basic concepts that we want to write here. So, just like we have voltage gain, we also have current gain. Okay, so the current gain, we define it as AI, and it is equal to I out over IN or II, and it is in amps per amps. Okay, and also we have power gain. مثل ما في عندنا voltage gain, we also have power gain, and the power gain AP is equal to power of the output at the power of the input, and we can express it as VO times IO over VN times IN, and the unit is watts per watt, and this can be expressed as what? This can be expressed as AV, which is the voltage gain times the current gain. Okay, so just like the voltage gain can be positive or negative, AI also can be positive or negative, but the power gain is positive, but mostly AP is positive, or most of the time positive, because it is the product of the gain of the two gains. Okay, so AP is usually positive. Okay, another definition which you are familiar with is the representation of the gain in volts per volt, amps per amps, or in decibels. Okay, so by decibel, you are all familiar with the decibel term, but let us see how we convert the absolute value of the gain So we use it to express gain in dBs, and for AV in dB, okay, it is equal to 20 log absolute value of AV, and this is the AV in volts per volt. The same for AI in dB, it's equal to 20 log the absolute value of AI, which is expressed in amps per amps. And for AP, which is the power, in dB, because it's the product of the two, it is 10 log of absolute value of AP in watts per watt. Okay? And the log is log base 10, so all the logs are base 10. Okay? So, for example, we can give you a question where we say, and you can try to solve this on your own later, or let us walk through it. So let us say, for example, that if we know that AP is equal to 10 dBs, okay, and we know that AI is equal to 2 dBs, find AV in volts per volt. Okay, find the absolute value of AV in volt per volt. Okay, so for this, we can find AP in watt per watt, we can find AI in amp per amp, and then divide them and get AV in volts per volts. Okay, so we can say 10 is equal to 10 log base 10 of the magnitude of AP in watt per watt, and we can find it, and then we can do the same for AI and then say that AV times AI is equal to AP. Okay, great. Now note that if the quantity in dB is negative, this is an important note, if the quantity in dB is negative, then this means that the absolute value of the gain in volts per volt, for example, or amps per amps, or watt per watt, the absolute value of the gain is less than 1. Okay, so what we are going to do next time is we are going to take several examples along this line, and we refer to this amplifier that it is attenuating. So the amplifier in this case is attenuating. يعني بدل ما growing the signal, it is really shrinking my signal. Okay, so we will stop here for this time. Thank you for your attendance, and we will continue next time with examples, okay, from here, so that we can practice a little bit and then continue with the amplifiers. Yes, I will upload, Khalid, the notes to Moodle. I will save it as PDF and upload it to Moodle, and I will upload the lecture also as well to YouTube. And in case I forget to record at the beginning of the lecture, I should not, but please remind me every lecture.